There were some questions about going through and doing the calculations. So I wanted to go through them a little bit, maybe more methodically, and just show you what things are. So rather than just pulling numbers from one particular group, everyone can see the numbers, everyone can refer back and go, oh, okay, that's where that's coming from. So to use numbers, I'm just going to go through and use the example that was in the lab report or in the lab handout. So the lab handout does go through and talk through this. I'm just going to go through and talk through it as well. Sometimes it's actually easier to see it than to kind of work through the math. But we have this particular circuit. We have 3 voltage sources, E1, E2, and E3. We have 3 resistors, R1, R2, and R3. So, okay, we have 2 loops, and we have 1 independent, or if I'm remembering right, I think the lab handout calls these essential nodes. So we'll need 3 equations to go through and handle everything that we have here. 2 based on the loops and 1 based on the node. Now again, a node is where 3 or more wires connect. So the nodes that we have in this one would be here and there. Now, if I know what's going into and out of this node, I can also figure out what's going in and out of that node. So I don't need both of them. One or the other is enough. In fact, if I had 5 nodes, I would need 4 of them. The last one is not independent of the others. The last one would be considered dependent. So, since I just need one of these nodes, let's just work on the one on the left. So, and maybe some color coding might be helpful. Do this in blue. So, I guess there's 2 H's in Kirchhoff's. That's why I wasn't looking right earlier. Kirchhoff's junction rule. Now, this is the one that we talked about in class. What goes in must come out. So let's look at what's going into that particular node. Well, we have current I1 that if we follow it along would be going into that node. Current I2, again, the arrow shows that it would be going into that node. And current I3 also is on a collision course for that node. So we can say that I1 plus I2 plus I3 equals 0. Now, in terms of the real way the world works, we know that we can't have all currents going in and no currents coming out. Showing these all as positives where they're going in means that we've assigned one or more of the directions incorrectly. But it's okay. It's okay. When we calculate it, we'll simply end up with a negative current on one or two of these. So this is our first independent equation. So let's look at the next independent equation. And I'll do this one, in red. So Kirchhoff's loop law number 1. So we have a loop here that's defined as loop number 1. Now, as I talked about in class with the loop law, if we go around a complete circuit and end up where we started, then the entire circuit has to have a 0 change in voltage as we've gone around. Well, in loop 1, I simply need to pick a starting point. Now, I could pick a starting point like right here, but sometimes I think it's easy to pick a starting point that is, maybe at a corner or something kind of visually easy to remember. I started there. And according to this loop, now it was already drawn in for you which direction we want to go around. If you wanted to go counterclockwise, you'd end up with the same answers at the end of the day. So it doesn't really matter. You just have to be consistent. You can't go clockwise part of the way and counterclockwise on the bottom half of the loop. You can't do it that way. You have to be consistent all the way around. So let's be consistent and go around our circuit. So the first thing, as I'm going clockwise, is that I'm going to be going through this power source. Now, we showed power sources as two lines of unequal length. The longer line is the positive, the shorter line is the negative. So we're going through this power source, this battery, backwards. So I'm going to have a negative 20 volts that I'm dealing with here. As I continue through my circuit, I'm going across R1. But I'm going in the opposite direction of the current. Now, normally we talk about a voltage drop as we go across the resistor. Well, if I'm going backwards across the voltage drop, it actually ends up being a voltage increase. So I can go down a water slide and I'm losing potential. If I went in reverse and went upstream against the current of the water slide and went back up to the top, I'd be gaining potential. So I would have a plus I1 R1. So it's current I1 across resistor R1 that I have here. Going again across or in clockwise formation, I hit another power source. Again, the long line is positive, the short line's negative. This one, I'm actually going across it in the right direction. This one's going to help push and increase my voltage. So I'm going to have a positive 18 volts as I go across that power source. As I continue to go across this resistor, I'm traveling in this particular leg of the circuit with current I2, and I'm going in the direction of the current, so it'd be minus I2 R2. Again, we're setting it as negative if we're going in the direction of the current because we have voltage drops, or positive in the opposite direction of the current because we're kind of swimming upstream. We're going to be gaining potential in that particular process. And then I would end up back at my starting point. Now, I could go through and actually plug in some numbers. I actually know what R1 and R2 have for values, just as I probably should have treated this as minus epsilon 1 and plus epsilon 2. I probably should have used the variables since I was using the variables on those. Okay, so kind of pre-plugged in those. My I1, I don't know. So I1, but R1 is 7 ohms minus I2, and R2 is 5 ohms. Okay, so now we have our second independent. Actually, I can simplify that just down a little bit more. Let's call it plus 7 ohms times I1 and minus 5 ohms times I2 equals minus 2 volts. Okay, so now we have our second independent equation. Third independent equation coming up. And this one, let's do in purple. So now I want to do Kirchhoff's loop law number 2. So now I'm down here in loop 2. I have a clockwise pathway. First thing I see, positive, negative, I'm going to be going backwards. Well, actually, no. Let's pick a starting point. I'll pick that node as my starting point. So, I'm going clockwise through this. I pass across R2. But I'm going opposite the direction of I1, so it's plus I2. Oh, sorry. Opposite direction of I2. I2, R2. I go across the power source, but opposite the normal direction. It would be positive if I was going to the left. It's negative if I go to the right. So negative epsilon 2. We go across the next one. We are going in the direction of I3, so minus I3 R3. We're going in the direction of that power source. So we have the positive, we have the negative. So plus epsilon 3, and then we're back up to our starting point. Okay, so I can plug some numbers in. I know I have R2 is 5 ohms. So plus 5 ohms times I2. R3 is 3 ohms. Epsilon 2 minus 18 volts and plus 13 volts, or minus 5 volts altogether. So we now have our third independent equation. And using the spreadsheet that I made sure I emailed it out to the entire class, we have these. Going back and grabbing these equations. There we go. I have this equation. Copy. Paste. Make it a little bit smaller. This is this equation. So we have a coefficient. We have one I1. We have one of the I2s. We have one of the I3s. The one, the one, the one. And, 0 volts involved. It's just current in and current out. Looking at our second independent equation. That's this equation. So, okay. So, one slight hiccup here. But I want to go ahead and grab the third equation and then talk about what happened. So, third equation, and I'm going to clean this up a little bit on the next page. So clean that up a little. Okay, so this one is this equation. When I was doing these, I set the voltages on one side. What I should have been doing to keep my signs consistent, so I should have been doing this all equal to 0. So if we go around the circle, if we go around the loop, we should end up with 0 voltage change. All of these change voltage along the way, but the sum of all those voltage changes should be nothing if we end up exactly where we start. But as I bring those to the other side, I'll end up with a negative term on half the equation. And that's what's happening here. So these should be the opposite sign of what I had initially. So a negative and a positive, and likewise, these should be the opposite sign So negative and positive. Okay, so, but we don't have any I1s in this equation, so it's a coefficient of 0. That's how you make something disappear mathematically. You multiply it by 0, it goes away. Likewise, there's no I3s in this one, just a coefficient of 0. As you use the resistances, now, again, we were using the values that were given on the graph. For your particular circuit, you'll have the resistances that you measured with your multimeter. You can use the colors from the bands, but the measured ones from the multimeter, if you have those numbers, should be more accurate and would be preferred to use versus just reading the band colors, because they do have a plus or minus tolerance. It's not exactly on the nose for what the bands say. It could be plus or minus 20% from that. The multimeter will give you the actual value for that particular resistor without any uncertainty, without any wiggle room. Or at least with a lot less uncertainty, I should say. So, once you plug these in, you'll calculate the Excel spreadsheet will automatically calculate the currents for you. Since we were dealing with things like 5 ohms and 3 ohms, there's going to be a decent amount of current, using these numbers. Your resistors are probably going to be more in the 400 to 2000 ohm range. You're going to have more on the lines of milliamps, like maybe 2, 3, 5 milliamps, versus having hundreds of milliamps. But going back to our junction rule, we said all 3 of these were positive because all 3 of them are going towards that node that we picked to be our independent node. Well, down here we can see that one of those calculated out to be a negative current. It's actually going the opposite direction from what we anticipated based on the arrows that we drew. And I3 is actually going the opposite direction. We knew at least one of them had to be going in the opposite direction, but now, based on these calculations, we can actually see that it is in fact I3 that's doing it. Now, if we were going through and working these kind of problems out for ourselves, how would you do it? So, if you were going through and having to not rely on an Excel spreadsheet to do the calculation for you, how would it work? Well, we would start off with our I1 plus I2 plus I3 equals 0. We would have our negative 7 ohms I1 plus 5 ohms I2, negative 7 ohms times I1 plus 5 ohms I2 equals negative 2 volts. We would have our negative 5 I2 plus 3 ohms I3. Negative 5 plus 3. Negative 5 ohms I2 plus 3 ohms I3 equals negative 5 volts. So I'm taking these 3 equations and I'm going to go through and start substituting in. So I know I1, if I use this equation to rearrange it, I1 is equal to minus I2 plus or minus I3. So I could plug that in to the next equation. So I'd have my negative 7 ohms times negative I2 minus I3 plus 5 ohms I2. Well, now I'm down and equals minus 2 volts. Well, I could solve this for, let's say, I3. Or I could solve it for I2. Simplify this down a little bit. So I would have plus 7 ohms times I2 plus 7 ohms times I3 plus 5 ohms I2 equals minus 2 volts. Well, I have a couple of I2 terms here that I could combine. So plus 12 ohms I2 plus 7 ohms I3 equals minus 2 volts. So solving for I2, that would be minus 2 volts minus 7 ohms I3, all divided by 12 ohms. Well, now I could plug that in for my I2 here, and then have an equation that's only in terms of I3. So, plugging that in, I'd have my minus 5 ohms times all of that plus 3 ohms I3 equals minus 5 volts. And simplifying this down a little bit, I could go through and say, multiply that across the top. 10 ohm volts minus 35 ohms squared. No, plus 35 ohms squared. I3 divided by 12 ohms plus 3 ohms I3 equals minus 5 volts. Okay. Simplify it down a little bit more. I have 10/12 volts. So the ohms would, so breaking it apart into two pieces, I'd have 10/12 ohm volts over ohms, but the ohms would cancel, plus 35 over 12 ohms times I3 plus 3 ohms I3 equals minus 5 volts. Okay, because again, the ohms squared divided by ohms would just leave me ohms. combining these, I'd have 35/12 plus 35/12 ohms plus 3 ohms. I3 equals minus 5 volts minus 10/12 volts. So I3 would equal, so simplifying that down, that's 5/6. So, let's see, bring up a calculator. Okay, so minus 5 minus 10 divided by 12. So that would be negative 5.83 volts divided by 35/12 plus 3, 5.92 ohms. And if I divide those two out, that divided by that, it gives me negative 0.986 amps, or negative 986 milliamps, and negative 986 milliamps for I3. So you can go through and work these out as series of equations perfectly fine. Now, once I had I3, I could plug it back into this equation to find I2. Once I had I2 and I3, I could plug it back into this equation to find I1. I mean, it takes time. I'm not going to lie about how much time it takes. This takes time to just crank through the algebra. But it's just, once you have the equation set up, it's just a bunch of algebra and simplifying down, substituting in, simplifying down, substituting in, until you get it down to a single variable, and then you just solve for it. So I know I was going through the calculations fairly quick today. I had a couple people that had appointments that I was trying to make things go a little bit faster so they could get out without having to feel like they had to leave early. I apologize if trying to go faster to help things move along faster actually ended up making things more confusing. Did not mean for that to happen. I did it with the best intentions, but sometimes those plans do backfire. But hopefully going through this a little bit slower, a little bit more methodically, helps point out kind of what the thought process is, how we handle the signs, how we handle the data. Of course, use your own values for your own resistors as you're setting these up. But whether you're setting up circuit 1, whether you're setting up circuit 2, it's the same thought process that you would go through in each of those cases. So again, hopefully this helps. I'm going to go ahead and stop it here just so it doesn't turn into too long of a video. And we'll see you tomorrow in class.